Hey everyone, this is Muhammad.nadeem and welcome to my YouTube channel. Today the topic of presentation is magnetic flux. As we know that if we provide the potential difference to a conductor, the magnetic field will produce around that conductor. And if we put that conductor inside the external magnetic field, the force F will be applied on that current carrying conductor because the magnetic field produced from that current carrying conductor will be interact with the external magnetic field, and due to which the force will exert on that current carrying conductor. And in the previous video we determined the magnitude of the force exert on the current carrying conductor inside the external magnetic field, and where we saw that force, the magnitude of the force, is depend upon the current in the conductor and the length of the conductor which is exposed to external magnetic field and the strength of external magnetic field, and similarly the theta present between the magnetic induction and the length of the conductor. And here if we take the other parameter as constant, and here I can write that f is directly proportional to the length. It means that if we increase the length of the current carrying conductor which is exposed to external magnetic field, then the force will be more exert on that conductor. Our desire is to have more force on that conductor, so therefore we are using the coil inside the external magnetic field. So these are different types of the coils, and here the coil is actually a conductor, but that is arranged in a small area. The large conductor is designed in a small area, will make a coil. So if we put that coil inside the external magnetic field, if I place on this side of this coil is north and this side is a south, the magnetic field lines will originate from the north and that magnetic field lines will terminate on this south. So these are the magnetic field lines. Here, the coil present inside in this external magnetic field will have some area. So this is, let's say, this is that coil. This is the one face of the coil. This is the other face of the coil toward the left side, and this is the other face of the coil towards the right side. So this face of the coil will have some area, and the magnitude of the area is given by multiplying the length and the width, and the direction of the area is given by perpendicular to this area, this face. So here the direction of the area, and on this face the direction of the area is given by this. So this is the direction of the area, and on this side the direction of the area is also given by this, and on lower side the direction of area is downward. Let's label this as, this is what this left side of the coil is considered to be a 1, and this upper side of the coil is considered to be the 2, and this is the third one, and this is the fourth one. So here the external magnetic field lines will pass through this area and also interact with this area and also pass through that area. So here the concept of magnetic flux is come into picture. So the number of magnetic field lines that pass through a specific area. So here this is the area, this is area, and this is area. The number of magnetic field lines, the number of magnetic field lines are the magnetic induction that pass through the area, and that area is placed at some angle. So that area is placed at some angle. This is called the uh, magnetic flux. So here in this scenario, the magnetic field lines that are originating from the north are passing through this left side. So here are passing from this side one. So the magnetic flux from the side one, magnetic the magnetic flux from the side 1 is given by magnetic flux is equal to B A cos of theta. And here the direction of the area is outside, it is toward the left side. And here the direction of the external magnetic field is towards the right side. So here the angle will be 180. So this is equal to BA cos of 180. And cos of 180 is equal to minus 1. So therefore it will be equal to BA and this is minus 1 which is equal to minus BA. Similarly, the magnetic field lines that are passing through this upper area is given by this. So here, this is the first case, and in the second scenario, we have the magnetic flux. The magnetic flux from the side 2 is given by the same formula. Phi is equal to BA cos of theta. Here the direction of the area um, is in this side, and the direction of external magnetic field is in this direction. So here the angle 90 is present between the external magnetic field and the direction of the area. So this will become here we will put B A cos of 90, and phi is equal to cos of 90 is equal to 0. So B A into 0 which is equal to 0. The flux and this through this side of the coil will be 0. And similarly, the flux through that side, the side 3 is given by this. The formula of the flux is phi is equal to B A cos of theta. And here the direction of the this side of coil is towards the left side, and here the external magnetic field is also directed toward the left side, and here is the angle theta is equal to 0 present between the direction of the area and the external magnetic field. So here we will put that B A cos of 0 which is equal to BA. Cos 0 is equal to 1. And for the for the lower side, the angle will be 90 because this is the direction of the area and the direction of the external magnetic field is this. So here the 90 angle will be present. So for the last side, phi is equal to BA cos of 90 and which is equal to 0. So from here, we conclude that magnetic flux is actually quantify us that how many magnetic field lines are passing through a specific area. So here a large number of magnetic field lines are passing from the left and the right side of the coil, but from the top and the bottom side of the coil, there is no magnetic field lines passing, because this area is present parallel to the external magnetic field. Here the more magnetic field lines are passing from this side and from this side of the coil, as compared to this side and this side. So here on this side, the magnetic field lines are moving parallel with this face of the coil. Therefore, no magnetic field lines are passing through this face of the coil, and therefore the magnetic flux from this side will be zero. And similarly, the magnetic flux through this side is also zero. Why we study the magnetic flux? Because in the previous video we discuss about the conductor only. So from there, if we find the magnitude of the force on that conductor, we take the clue here that this force is also depend upon the length. So for that, we take the long conductor, and we design that long conductor in a small area. We call them as a coil. So this is different types of the coils. The magnetic field line will now pass through the coil, and the coil will have some area. So the number of magnetic field line passing through the area depend upon the angle present between the area, the direction of the area in the external magnetic field. And similarly the magnetic flux is also depend upon the magnitude of the area. It also depend upon the magnitude of magnetic induction. Magnetic induction is actually the amount of magnetic field lines that are passing through the area. So this was the simple explanation of the magnetic flux, and I hope you got my point. So that's it, guys. Thanks for watching.